The term biosensors isn't something that you'd hear every day, but a lot of people around the world and a lot of medical organizations use this tiny device. In short, biosensors is a device that basically analyzes the concentration of an analyte. For example, in diabetes, a patient would use a glucose biosensor, which basically identifies the glucose levels. In this case, the analyte would be the glucose. There are different types of biosensors, and one of these includes electrochemical biosensors, which are actually one of the most common types. An electrochemical biosensor is a class of biosensors that work based on an electrochemical transducer, and this component of the biosensor helps convert changes in form of an electrical signal, which is directly equivalent to the concentration of an analyte. To put it simply, this type of sensor works with the help of gas diffusion. Gas finds its way to the outlet of the membrane on the top of the sensor housing. Once the gas finds its way to the working electrode, an electrochemical reaction occurs. Electrochemical sensors are mainly used for detecting oxygen or toxic gases. More specifically, they're used to measure the concentration of a specific gas within an external circuit. This is done by a method of oxidation and reduction reactions. Though these terms might sound a bit scary, don't worry, it has a super simple meaning. Oxidation is basically the change in a chemical substance because of the increasing amounts of oxygen. Meanwhile, reduction is the opposite of that. Reduction involves a half reaction involving a decreasing amount of oxygen levels, usually because of it gaining electrons. No matter the type of sensor, all biosensors use a specific 3-step process in changing the analyte's concentration to something that is readable, such as numbers, graphics, or just converting those energy into a different form. The first step in this process is known as biorecognition, which is a process of signal generation between the interaction of a bioreceptor and an analyte. The second step of this process is called signalization, and this involves the role of a transducer, which is a component of a biosensor, and it converts the biorecognition event into a measurable signal. The very last step of this process is quantification. The process signals are then quantified by the display unit of the biosensors. But here's what's lacking in an average electrochemical biosensor. First of all, they're expensive. The prices of an electrochemical biosensor ranges from $1,000 to $5,000. And on top of that, they're kind of inefficient. They're not accurate enough and the information doesn't go as fast. However, a material that could be combined to this technology to improve it could be electroactive polymers. The unique electroactive properties of conducting polymers allows them to prepare biosensors that enable real-time point-of-care testing. Potential advantages of using these devices involves low cost, low detection limit, resulting in increased access of treatment. So just a bit of background information. Polymers are these long repeating chains of molecules. Meanwhile, electroactive polymers are the same thing, except these polymers change in size or shape when stimulated by an electric field. The mechanism of conduction for most polymers involves the removal of electrons, which is known as p-doping, and this results in a formation of a radical cation known as polarin. Normally, the cation is distributed among 3 to 5 quinodal rings. This is followed by removing the second electron in the polymer chain, resulting in a dication, also known as biopolarin. This accounts for the transport properties of conducting polymers. The spineless bipolars become mobile under an applied electric field, especially with high doping levels, where the screening of the Coulombic attraction with counter ions, resulting in a fast and more effective transport of the current. But with all the new changes, biosensors are going to have to adapt to conducting polymers, and for that we can use 2 different types of methods. For the electrochemical characterization method, we can use amperiometry, which is the detection of ions in a solution based on an electric current. Amperometric devices continuously measure current that has been resulted from oxidation or reduction. This is measured by the reduction of oxygen at a platinum working electrode, and the current is measured at a constant potential. Now for biorecognition molecules, we can use antibody-based recognition. One main advantage of the antibody-based recognition method is that the analyte, which is the antigen, does not have to be purified prior to the detection. Conductive polymers are like Superman at a molecular level. They have the ability to interact and engage with organic or inorganic materials to provide high selectivity or sensitivity, therefore making them a prime substrate for detection in biosensors. By using conductive polymers for biosensors, it can open doors to different applications such as medical monitoring devices, tissue engineering, or even early detection for diseases such as cancer. This small device is simply designed and it uses a cost-effective material, which can revolutionize healthcare and also help us understand science better.